Okay. Okay, service is now done, and I want to check your attendance. So this is lecture 13. Lecture 13. 13. 이재혁 씨? 네. 고하늘 씨?
네.
네. 심준호 씨? 네. 이승빈 씨?
네.
이정태 씨? 네. 이충하 씨? 네. 정상아 씨? 네. 홍주표 씨? 김민선 씨? 김유신 씨? 김유신 씨? 배민현 씨? 배서령 씨? 서하연 씨? 조재현 씨? 네. 최승규 씨? 네. 김성수 씨? 네. 미스터 마니케르? Okay. Now let's get started today. Okay, first of all, okay, so voice is recorded, and yes, this is lecture 13. 13 will be the end of our first half. So lecture 13. But before starting our lecture 13, so I wanted to ask you whether you have any question about our homework problem in our previous lecture, or so we are quite close to the midterm examination, so maybe you have some questions about this the first half of our lecture entire semester. So could you please give me a question about any topic? So okay, so up to now nobody has reported me about the COVID-19 positive case, so I think that we are quite close to the offline examination, but nobody knows actually. So nobody knows, so I will just wait for the last minute. So at the last minute, if somebody claims that, oh, I got positive, then we will cancel the examination, and the programs will be distributed as a homework program. So okay, so that was one thing. And any question from our students? Okay, so usually I got plenty of questions only just the last lecture before midterm examination, but I think that this is one exception. So this year we have an exception. Okay, so now let's go to lecture 19. But one thing I wanted to recommend you to is please visit the archived repository for our lectures. So there you can find all of midterm examination and final examination. They are all stored and you can directly access it. Even you don't have to log in, so anybody can access it. And I wanted to strongly recommend you to at least the coverage of our lecture progress. Please try to solve the problems. So you know that in this semester, my lecture, on-site lecture or online lecture, were devoted to how can you improve your understanding of the topic. So you feel that this course is more related with understanding and yes, some feelings about the topic. However, the essence of this topic, this course is also in the calculation or get strict number. number is quite important for this course also. So I once again, although I have not gave it as a homework problem or some examples, but you have plenty of resources already available to you. So please visit those archived repositories. Okay. So are you doing such a thing or no? Okay, but anyway, it will be good for you to take the midterm examination. And one thing I wanted to tell you is here, for example, in these days we are now using some graphs. So in this offline lecture I show you some graphs, and those graphs are also known to you, so you can also find that. Okay, if you go to the subdirectory of our repository resources, then you can find the L12 and L13. So L13 contains the figures which will be used in today's lecture, and L12 contains the previous graphs you have seen in the last lecture. Okay, so I think that at least I think that at least it is my responsibility to open all of the resources to you. So your responsibility is to study them. So I will open everything. So please try to have the material and try to understand those ones. Okay. So if you don't have any further question, okay, then I will just dive into our last lecture before midterm examination. So you know that we had a long journey to find out a nonlinear component called PN junction. PN junction is one way to fabricate a circuit component called diode simply means that two-terminal device. Di means two and os is a terminal, so simply it means that there are two terminals. However, when you say diode, it is strictly representing something like this. For positive bias, usually called as a forward bias, and negative bias, usually called as a reverse bias. So for forward bias, it conducts and it doesn't conduct in the reverse bias. So we spent almost several lecture hours on this one, and fabrication itself was amazingly simple, and we have studied the equilibrium property and existence of depletion layer, so in order to cancel out the current conduction. Then after that, when we apply forward bias, then excessive diffusion current will occur. And also when we go to the negative bias, reverse bias, and that diffusion component is minimized. However, since the current is more or less balanced, so we have almost no current conduction in reverse case. And how about lecture 12? So at lecture 12, okay, now we have some component called a diode, and its IV characteristics, its terminal characteristics can be well approximated as like this. So as a function of applied voltage, our terminal current can be obtained as something like this. So exponential. So important quantity or important dependency is exponential dependence on the applied voltage. So if we apply slightly larger voltage to our diode, then we will have much larger current. So that is the key point of this diode operation. And here you can see that we have certain normalization. So V is normalized by what? By the summer voltage, and typical value at 300 Kelvin was just 2585 millivolt, not volt, millivolt. So this is quite a tiny voltage. So if you apply just the additional one summer voltage, then your current will be increased by factor of natural number E. So you have quite a rapid increase of terminal current when you slightly increase your current or your voltage. So we have seen that there will be certain rule of thumb like this, 60 millivolt per decade. So in order to increase your terminal current 10 times, decade means that one order of magnitude increase of your terminal current, and you have to apply 60 millivolt. So 60 millivolt, is it large or small? So it depends. If your maximum voltage is just for example 0.5 volt, then 60 millivolt cannot be regarded as just a negligible one. However, if you are talking about the 5 volt technology, so your voltage swings from 0 to 5, then what will happen? Maybe you can say that 60 millivolt is just around just 1.2% of your voltage swing. So maybe that can be regarded as a really small one. So previously 60 millivolt per decade was quite acceptable and everybody were happy with this number. But nowadays this 0.5 is not on exaggerated value. So we are around the world of 0.7 volt or 0.65, even 0.6 volt. So we are quite close to 0.5 volt. So in this case 60 millivolt per decade, that is too how can I say, too moderate. So we wanted to have even steeper slope for our IV characteristics. So people think that, okay, if I can have, for example, 30 millivolt per decade, oh, what will happen? I will be very happy. But it is not easy to achieve this one, because the physical origin of this 60 millivolt per decade is, yes, this dependence, exponential V over Vt, and this one is exactly follow the rule of electron distribution. So in nature, if we are placing our electrodes at 300 Kelvin, then actually it follows a certain rule exponentially depending on the energy. So that is the reason why we have this kind of behavior. So it is very difficult to overcome 60 millivolt per decade rule. But anyway, you have to understand, if we have not scaled our voltage too aggressively, so if we are talking about the less modern technology, then maybe this 6 milli electron volt per decade can be regarded as a quite steep slope for our current increase. Okay, so any question? So please interrupt me anytime. Then at the end of our lecture 12, what was it? The topic was like this. Now we can think about a diode and a resistor, and we can apply certain input voltage, and also we can apply output voltage. And I remember that at the time I have made the comparison between this diode and resistor circuit and two serially connected resistor circuit. So in this case, if we are talking about this two resistor case, then we can easily find that, okay, input and output relation is just a linear relation. If we have, for example, 1 volt, yes, let's assume that we have a 0.5 volt, then if we just increase it by factor of 2 volt, then we will have just 1 volt. They are linear. Okay, it is quite understandable. However, point is, here, let's say that here we have 1 volt. For example, let's say that this is just 0.2 volt. Yes, let's assume. Then if we have such kind of thing, if we increase by factor of 2, now we have 2 volt, then what will happen? if this system is really linear, then we can expect that, okay, since input voltage doubled, output will be doubled too. But you know, this is completely wrong. Yes, because our element called diode really behaves non-linearly. So at the end of our lecture, previous lecture, we have find out how can we rigorously solve this problem. The way to rigorously solve this problem was quite straightforward. So apply the KCL to this node, and KCL simply means that the incoming current and outgoing current should be perfectly balanced. So it means that we have to make we have to make complete balance between diode current and resistor current. So of course the direction is important. However, in this case we believe that yes, this is a better direction for diode current and resistor current. After that, we will have certain simple rule like V out divided by our resistor R. Yes, that will happen. And here we will have IS and exponential something. Yes, we have something here, but what is the something? So that should be the voltage difference between the anode voltage and cathode voltage. Anode voltage is given by input voltage, and cathode voltage is determined by output voltage. So we will have this one. So once we take this V in as a given number, like 1 volt, 2 volts, 3 volt, then the remaining unknown variable is V out, and you can see that this one really contains the numbers like V out and V out. You can try to find out the solution. Okay? Then at the real end of our previous lecture, I just introduced the method, numerical method to solve this system. So that was called as what? Called as Newton method. So if you have done our previous homework problem, then maybe you have studied what is the Newton method, and if you have done it correctly, then now you can solve certain simple system starting from certain initial guess, and by iterating this method, eventually you will get very good solution for this non-linear system. Okay, so I think that is the story up to now. So do you have any question about our lecture progress? So okay, so it is always welcome to have a question, and I will be quite happy to listen to your question. Okay, then if you don't have any question, then let's go to today's lecture. Yes, so maybe it is not very convenient for everybody to build a nonlinear equation solver for these cases. So we have invented a program. We means that, no, not me, not you, but several decades ago. So clever guys invented a software called SPICE or its variants, and when you use SPICE, you can always get the solution about this one. But today I wanted to explain how can we find out an approximate solution about this system. The numeric value itself can be found by the SPICE, but before starting our SPICE simulation, we have to understand the qualitative behavior of this system. So that will be the main topic of our today's lecture. Okay, so I think that you have no question about this one. Then why don't you just have a look at these graphs available to you. Okay, so this is the graphical representation of our system. Here I assume that there is certain R values. For example, we can so we can think about a case where R is 0.5 kilo ohm, or sometimes we can think that R is 1 kilo ohm and R is 2 kilo ohm. It's up to you. You are a designer, so therefore you have some right to change the parameters of your circuit as much as you are allowed it. So, what will be the best performance for your design? That should be designed by yourself, and you have to find out the best value for your R, for example. So, therefore, in order to find out that best R value, now you are trying just to sweeping your R value starting from 0.5 and increase it by 2 volt, and you will get the solution about this operating point and try to find out the best design. So let's assume to such a typical use case of your circuit design. So now I assume that there is a certain diode, yes, so diode, and this diode has quite a small resistance, and now we have applied 1 volt. So here we have a case where we have applied 1 volt, and here this dashed line, green dashed line, is corresponding to a case where we have applied 1.5 volt. So before starting all kinds of discussion, I have to explain what are they. So this, and this. Okay, so the x-axis here is output voltage. So output voltage is simply V out, and this is, yes, representing the node voltage at that node. So you can immediately understand V out is corresponding to what? Corresponding to the voltage applied to our resistor. So this curve, or these curves, simply means that we have a line like I equal to V out divided by R. So now you can understand this black, red, and blue curves are corresponding to IV characteristics of our resistor. Okay, so for example, if we apply, if we apply one, so I made a mistake, sorry. If our output voltage is 0.8 volt, then if we have 2 kilo ohm, then we will have a certain current like 0.4 milliampere. And if we have 1 kilo ohm case, yes, then we will have 0.8 milliampere. That's it. So this is just IV characteristics of our what? Our resistors with various values. And now we have to also consider diode current. So green line is corresponding to diode current. Of course, you can say the diode current is given by IS, yes, exponential V Vt minus 1. So why do we have such a kind of seemingly just mirror the image of our exponential function? You know that actually IV characteristics of our diode just looks like from your side like this, but now you are looking at the curves like the other way around. Why? It is because this x-axis is corresponding to V out, not your applied bias. So let me just give it more clearly. So exponential, here we have to have V in minus V out, Vt minus 1. And in this graph, what is the x-axis of this graph? Yes, now you understand. This guy is used as x-axis variable of our graphs. So now you can think that this is almost corresponding to exponential minus v out. Okay, of course it has certain coefficient corresponding to exponential something. So this is corresponding to our diode current. And please note that what was the KCL applied to our output node. KCL simply states that diode current and resistor current should be perfectly balanced. So means that, for example, if we consider, for example, this point, yes, if we have V out equal to 0.3 volt, then we will have a certain value for our diode current, and also we will have certain value for our resistor current. And are they equal or not? So obviously they are not equal. It means that at the value of exactly 0.3 volt of output voltage, then KCL is disobeyed. That is wrong. We have to find out a position where two curves are meeting together. Only at that point our diode current and resistor current are the same. So could you please find out the point where those graphs are meet together? So you can easily find that. In the case of a 0.5 kilo ohm case, yes, that will be the point where two curves are meeting together. If we have, for example, 1 kilo ohm case, a red colored one, then you will have, yes. Also for others, you can find this point. Okay, so therefore, simply speaking, if you change your R resistance, then what will happen? Your output voltage will be slightly changed, slightly. But how slight is it? So you can see that although you have changed 4 times difference in your R, however, your difference in output voltage is relatively small, smaller than just 0.05, oh sorry, 0.05, less of around 50 millivolt difference for these three cases, although we have changed our resistance by factor of 4. Okay, so output voltage is more or less same. So simply speaking, without with a certain boundary, I can say that okay, V out is around 0.3 volt. Do you have any objection? No, it's not. It's not exactly 0.3. We have to find out 0.32 or 0.33. You may say so. However, if we neglect just second digit, then we can roughly say that okay, in many cases, this number is just corresponding to 0.3. So why do we have 0.3 regardless value of R here? We have quite much different changes. So now let's go to our circuit here. It simply means that now think about a scenario where we slightly ramping up the input voltage. Starting from 1 volt, we are now going a journey to 1 volt. So when we first increase our voltage from 0, for example, 0.1 volt, yes, we have slightly increased 0.1 volt. Then what will happen? You have a diode and you have a resistor. And the resistance of this resistor is fixed as 1 kilo ohm, 0.5 kilo ohm, 2 kilo ohm. It's given. And how about this PN junction, PN diode? In the case of diode, so around the 0 volt, actually it has quite close to perfect insulator. So when we compare the differential resistance between this guy and that guy, then we can certainly say that, okay, I will just dump all of my applied voltage to what? To this guy. So I can certainly say, if we have 0.1 volt, then output voltage will be just 0. So are you with me? That here, if we have 0.1 volt, then we will have just 0, very close to 0.0. Then if we assume that case, then we can say that, okay, 0.1 volt is applied to this guy, and almost 0 voltage is applied to this resistor, but it really satisfies the KCL because the extremely small difference is applied to our resistor, so it doesn't conduct error. And in the case of our diode, although 0.1 volt is applied across the diode, but diode is not turned on by such a small amount of applied voltage. So I will not conduct any longer. So KCL is still valid. Then you can now repeat this kind of description again. Until what? Until now your diode is close to its turn on voltage. For example, in this case, around 0.7 volt. So up to 0.7 volt, if you apply further and further voltage, then that applied voltage will be just dumping to your diode. So resistor does not take that additional voltage. It is because, let's assume that, let's say you have a 0.7 volt, and let's assume a case like, okay, now say I have a 0.3 volt and 0.4 volt. Wow, we are quite happy. But if we take it this way, then resistor will certainly allow strong current conduction, and diode still says that, okay, I'm just biased with 0.4 volt forward bias, and I cannot conduct any meaningful current. So still we cannot satisfy the KCL. So KCL is the rule we have to obey. So it's not possible. So up to certain voltage at which the diode is sufficiently turned on, all of applied bias will be just applied to diode. Of course, when I say that 0.0 volt, that does not mean that exactly 0.0. It is a value quite close to 0.0 volt, and also 0.7 volt should be regarded as 0.6999, something like that. Okay, but now think about certain turn on case. Okay, around 0.7 volt, now suddenly this diode becomes highly conductive. So if we apply additional voltage 0.1 volt to this guy, okay, as usual, I will take them all 0.8 volt, and the resistor have just 0 volt. Then what will happen? Now this device is highly turned on, and it tries to conduct a lot of current conduction. But resistor says that, the voltage across me is just 0, so I cannot conduct. It's not a solution of KCL. So what will happen? In this case, instead of increasing the voltage across the diode, instead we have to increase voltage across the resistor. So if the diode is reaching at its, for example, certain on voltage, the remaining voltage should be applied to here. Here means that V in minus V on. Of course, you can say that, okay, if the diode is exactly biased as V on, then current is just fixed and nothing will happen. But here we have implicit assumption that our diode is so much sensitive to its input voltage or its applied voltage. So just to give a small portion of applied voltage can increase its current conduction, and all other parts should be consumed by this resistor. So if we think this way, then we can find out amazingly simple way. Simply speaking, if our input voltage, is smaller than on voltage of our diode, so what is the exact value of V on? So please don't ask me that way, because you know that you have to now understand this V on is just one approximate value, and it can depend on device and it can depend on the situation. So whether this is 0.8 or 0.7, that doesn't make any sense. So it really depends on situation. But if we have a certain number, then if our input voltage is smaller than that, then we can certainly say all voltage is applied just to our diode, and we will have almost nothing. So the answer will be below the on voltage, the output voltage will be just 0. But if we go beyond this V on, then we can have the other way around. Okay, up to now we have spent all of our applied voltage or available voltage to diode. After that, now diode becomes too highly conductive, then all kinds of additional voltage should be applied to what? To this guy. So V in minus V on. So if we just draw these characteristics, then we can find a quite simple graphs like this. Let's just say this is V in of our system, so bias voltage for our diode resistor system, and if we draw V out as an output voltage or y-axis, then we will have something like this. Up to V on, we have just a horizontal line corresponding to 0 voltage. After that, we will have just a line like this. Okay, then my question is, what is the slope of this curve? So voltage curve. So we have some unitless slope, because voltage divides voltage, and the slope is of course 1. So additional voltage beyond on voltage is just copied into our V out. So maybe if you are interested with a certain so neural network or some fascinating things, then you will find that this curve is quite close to the certain thing called the LELU. So maybe there is a certain similarity, although their contexts are different. Okay, so then this is just a drawing, but why don't you just check whether my rough explanation is still valid or not? So I have prepared my simulation result. I just really simulated solve some equations for appropriate equations for this diode and resistor, and I will show it to you. So for example, this one is our beloved N plus P junction. So of course at the time we know that current is only calculated by ampere per square centimeter, so per unit density, unit area. So I just fixed certain area. So of course if you have a larger one, then the result will be slightly different. But anyway, the point is when we have a diode and when you have a resistor, then their input output characteristics. This is V in and this is V out. Just looks like this. This is not my hand drawing, but this is calculated the calculation result of a numerical solver, and you can find that it is quite good actually in this scale. So I have applied up to 3 volt, and below, for example, point something. So device is just or our output voltage is very close to 0, and only we have beyond this voltage, then we can have a curve corresponding to slope 1 straight line. Okay. Do you have any question about this analysis? So simply speaking, if you use spice, then you can get this curve. So that is the role of a circuit designer. But before getting this beautiful graph exactly, so you can have several digits in these numbers, and you can find out there is a certain 0.1% difference or 0.01% difference. However, before discussing about such kind of a small difference, please concentrate on the understanding the material in this way. Simply speaking, the diode should be understood as two-phase component. Two-phase means that when it is biased below its own voltage, you have to consider that this is just a disconnected, isolated one. And once you are beyond the case where your overall voltage is larger than V on, then your diode just only takes the voltage around V on, and all other additional voltage should be consumed by what? Consumed by other circuit components. Okay, so are you with me? So yes. So then let's think about this case. This is IV characteristics of our circuit. So it has its own name called so half wave rectifier. So here we have V in and V out, and this curve just to say that what happens if I apply 3 volt. If V in is 3 volt, then what will be the output? You can now say that okay, when input is 3, then that will be around 2. What happens if I apply 0.5? Then output will be just 0. You can answer in that way. Then now please concentrate on this part. Now instead of just applying 3 volt or 0 volt and minus 3 volt, from now on I will try to some interesting experiment from now. So starting from this one, I will just change my input voltage in a time varying. So if I do it in this way, as time elapses, my input voltage varies. Then what will happen? Sometimes it can reach up to 3, and sometimes it can reach minus 3. Then what will happen to this guy? When our input voltage is 3, then maybe we will have around 2 volt. And if we go to minus 3 volt, then maybe we will have 0 volt as an output voltage. So now you can easily understand this graph. The third one I have prepared. Yes. For same system, instead of applying certain fixed values, 3 volt, 2 volt, 1 volt, I just make a time varying signal. So this black curve just shows my input curve. So it looks like a very beautiful sinusoidal curve. So this is really purely sinusoidal curve. And your red line, how does it look like? So in this positive phase, now your output just follows the upper half of our sinusoidal wave. It is because you know that the characteristics of your circuit is just to copy the input with a certain offset, like a minus V1. So since minus V1 is around 0.9 or 1 in this highly idealized and narrow PN junction. But anyway, let's say that this is the amount of our V1, then you can find that this red color curve is just a shifted version of our input curve, black curve. Yes, previously we have black curve and just reduce it by amount of V1. Yes, and if we have a negative value, just cut it out. Then we will have this behavior. And how about this second phase? So, second half period. In this case, input voltage is clearly negative, and in that case, there is no chance for our diode to be turned on. So certainly the output will be clearly zero. So now you have this case. Once again, this is the result calculated from my nonlinear equation solver, not hand calculation. But point is, yes, our understanding without any without any calculation is well matched to the more rigorous treatment. So please try to get certain feeling about this system. Not calculation, but you have to understand that. Okay? Yes. So do you have any question? I think that this is the point where students should ask me many questions, but yes. Anyway. So
정확히 해석할 수 있는 게 다이오드를 약간 스위치처럼 생각해서 아니면 그 익스포넨셜 모델로 하면 해서 저렇게
oh, okay. So first, let me repeat his question once again. Then, yes, this is the result of our analysis. Then his question was, is this result is dependent on the assumed model for diode? For example, we can think about many different models, like just a two-phase model. One phase just completely turned on, and one phase highly conductive. That can be maybe the simplest one. And also we can think that exponential dependence. Yes, we can think about that one. And even further, we can discretize entire PN junction system into many pieces and solve physical equation, for example, continuity equation or Poisson equation inside this system. But in every case, we have the same result. So this is because, well, although inside our system there will be electric field and electrons and holes and they are moving, but if we just make an abstraction, then all of such a kind of complicated behavior can be represented as just terminal characteristics. When you apply certain voltage, then you will have a certain current conduction. That is one way of abstraction, and still that abstraction is good enough for our purpose. That's the reason why, regardless of the model applied, adopted in this calculation, you will get the same result. Okay, thank you for your really insightful question. Okay, so now think about this one. Maybe you remember our homework problem previously. I asked you something like this. When we have this kind of, or for example, if we have a red colored curve, then if we take the time averaging of our signal, then what will be the average value. So I asked you that question in our previous homework problem. In the case of black curve, since this positive part, the area below this curve, and the negative part, the area above this black curve, are perfectly matched. So when we calculated the time average over one period, then eventually we will get just 0. So it means that this purely sinusoidal component, sinusoidal signal, doesn't have any kind of DC component. But think about this red colored one once again. Here we have a certain contribution, positive contribution, and how about negative contribution? Nothing. So there is nothing to cancel out this positive contribution. So when you take the one periodic average, time average, then we will find that, okay, the voltage, output voltage, really contains the DC component, which was not available in our previous case. So simply speaking, now we have generated a DC component out of what? Out of purely AC component. That is the important thing. So simply speaking, I wanted to say, if you have a certain frequency omega, then if you just have a linear circuit, then eventually you will have a certain output. And what will be the frequency of this output signal? The frequency of your output signal is still f. If you insert, for example, 1 Hz signal, then you will always have just 1 Hz signal. For example, 60, then you will get always a 60. It is because, you know, if we have just a resistor curve, then you will have V out equal to just proportional to V in, and if your in is changing in 60 Hz way, then your output will follow exactly that way. But now you understand, if we have, instead of this linear system, if we introduce kind of a non-linear system, then now although we have applied just a purely sinusoidal one, but now we can, in general, we can generate many different components. But the point is, if you insert 60 Hz, then you cannot generate, for example, 59 Hz. No, there is no chance for us to have this kind of component. Or 61? No, we don't have it. The generated output voltage out of this nonlinear circuit will be, please remember this one, will be just integer multiple of our frequency. So simply speaking, if you have 60 Hz signal, then you will have 0 corresponding to DC, 60, 112, 180, 240, something like that. You can generate multiple of your fundamental frequency. So if you have a certain seed frequency as used as the input signal, then your nonlinear circuit will just make a variance of them, and all of them will have multiple integer multiple frequency of this frequency. Okay. So I think that if you have attended other courses like signals and systems, maybe you have heard about this information. So this is not related with only for our electronic circuit, but any kind of a nonlinear circuit behaves like this. Okay. So yes, Maybe you like it. Oh, previously I didn't have any kind of DC component, but now I have a AC component. Hooray! But one thing we have to keep in mind that here we have the dead zone. Oh, almost more than half of our time signal actually corresponding to 0. Okay, although we have positive signal, uh, positive average, but let's say that if you are trying to use it for your cell phone charging purpose, so will you like it or not? So your signal is always turn it on, turn it up, turn it up, turn it up. So maybe you don't like it as your DC signal. More preferred way will be just like this. You want to have such a kind of behavior. So I will just show you how can you achieve this kind of thing. So previously we had just a diode and resistor, and now we have V in, and yes, that was called as V out. So in positive voltage case, it's okay. So anyhow, it can copy and paste our input voltage. However, this period, the negative period, the behavior of our system is just to neglect the negative part. So how can we reduce such a kind of behavior? So if we just introduce additional load, capacitive load component here. So here we have R and C. Then what will happen? In the positive case, then diode will be turned on. Yes, and it takes just to be on. Then all other additional voltage will be used for this RC component. Then what will happen? Okay, this diode now becomes a really powerful current source. It can now just to supply certain current into this R and C. So through this R, okay, there will be certain current conduction. So the current conduction will be just given by V out divided by R. And it's okay. But pointed here we have C and C. If we have increased output voltage, it means that this capacitor really needs the charge accumulated across this C. Okay? So let's assume that, for example, a certain parallel plates, and if we have positive 1 volt, then we wanted to have the charge density corresponding to C times 1 volt. So if we want to have increased V out, then additionally we have to supply certain charges through this way. So not only this R, but this C can be a path for current conduction. However, don't worry about that. Now our diode is so powerful, so it can provide sufficient amount of current to this capacitor too. So if we have case, think about this one. For this positive case, so now this diode will turn on here, and it will conduct this current, and also this capacitor will be charged. So voltage is increased. And now think about the second phase. Okay, now the voltage becomes negative. Then how can you visualize it? If we have really negative value for V in, then it is clear that our diode doesn't any role as a current conduction path. So we can think that this is just a disconnected line. Then what will happen? Oh, previously we had a powerful background for our current conduction, and okay, give me any amount of current, then I will give it to you. So that was the role of our diode for forward or positive phase. But now in the negative phase, it cannot perform any role. Then in this case, what will happen? So when our V out is given by V out, then here we have a certain charge corresponding to C times V out. Yes. So for example, in this case, in this specific example, we have, for example, 2 volt. So we will have C times 2 volt. This amount of charge was stored in our C. Then what will happen? In this case, there is no diode at all, and now we have just R here, C and R. Then what will happen? That is just a typical situation where we have discharging the charge through our RC circuit. If we have RC circuit in this way, then what will be the time constant for losing our charge or discharging the capacitor? You can easily understand the product between R and C. RC constant will determine the speed of losing your charges. So in this case, yes, I have used 1 kilo ohm and I have introduced 1 millifarad, so which is an amazingly large one. So when you just make a product between 1 kilo ohm and 1 millifarad, then you will have just number 1 second. So please note that I just introduced those numbers to for visualize performance. Visualize purpose. So you know that. So millifarad is really large one in microelectronics, not in power electronics, but in microelectronics you never see like 1 millifarad. So usually you have a much smaller. But anyway, if we have such a kind of variables, then your RC time will be just 1 second. So you can see that within this 0.5 second, your charge will decrease significantly. So if we just let this voltage no longer positive part, then what will happen? There will be just a single decrease of your charge. However, now change the situation is changed again. Now diode just wake up and oh, what happens? Oh, you just lost my charges. Then I will give it once again. So this is once again charge it and discharge, charge it, discharge. That will happen. So if you have such kind of behavior, then do you like it? Yes, maybe. From the viewpoint of your voltage, output voltage, compared with the red colored one, your blue colored curve doesn't show much smaller variation. So previously your signal varies from 2 volt and 1 volt, up down. But now it moves from 2 volt to 1 volt, 2 volt to 1 volt. But is it good for your use? Maybe not. You need more flattened curve. So why don't we just increase our C values more? So I have introduced the green line corresponding to 10 times larger capacitance. So what will happen? Now it is difficult to fully charge this capacitor, but at the same time it is difficult to discharge this capacitor. So now we have a lot more capacity for charges, and for first half period it can collect a lot of charges in it. After that, the RC delay time will be increased by factor of 10, because previously it was, oh, so I made a mistake, so please. This is corresponding to 1 millifarad, and this is corresponding to 10 millifarad, so sorry about that, so please, this is a typo. So now we have 10 times longer RC delay time. So it takes much longer to discharge this capacitor. So before reaching at the certain way to completely lose the charge, our next period comes, then now it goes up and discharging, up, discharging, up, discharging. So now this difference, so usually called as a ripple, and this ripple is much smaller than previous case. Of course, now I'm saying that I have introduced a quite a simple switch or circuit. Looks like this: just one diode and having certain capacitive load for our output load. However, in reality, in order to have better output for this for this AC to DC converter, so usually we have to introduce additional diodes. So standard way is introduce 4 diodes into it, then you will have much better result for this positive signal, positive phase and negative phase. Please note that why we have to introduce 4 more or 3 more. So although here we have beautiful curve, however it's like this. Only positive part the diode works, and this negative part is just to try to maintain the collected charge. So this part we are earning, and here we are losing. Earning, losing, earning, losing. However, if we introduce a different diode with different connectivity, means that here we have a diode which is biased in that way. Okay, so it reacts to our positive bias only. If we have a negative half period, then it will not conduct at all. However, instead of that, if we have something like this, then what will happen? It will completely neglect the positive half cycle, but instead it will try to conduct when it is biased in its negative half cycle. So instead of having just a half cycle used for current conduction, this the opposite polarity can provide us better stable signal, output signal. Anyway, that is all for our lecture. Okay, so let me, we have only 5 minutes left. So therefore, I will just wrap up today's lecture. So say, in the first half of our entire semester, we have made certain lectures about PN diode, PN junction and diode, and example of a nonlinear circuit made of diodes. So simply speaking, so I think that the contents up to now, up to lecture 12 was already given to you. So let me just summarize today's lecture. So now we have sufficient knowledge on the PN diode, and when we try to understand PN diode or diode, then the basic way is, instead of using complicated numerical form, please try to analyze the system with a regional way. I mean that whether this device or this diode is turned on or turned off, please ask yourself that question. If you can ask that question, and if you can answer that question certainly, then you can greatly simplify the non-linear behavior of your circuit. For example, if this diode is completely turned off, then you can just erase it from your circuit. That is quite easy. And on the other hand, if you can certainly say that this diode is sufficiently turned on, then it will just consume only around 1 voltage of that diode. Of course, in order to conduct further, actually this diode should consume a little more additional bias voltage. But since it's incremental, required incremental additional voltage is so small compared with our voltage swing, like 3 volt to 5 volt. So we can certainly say that diode is much more or less biased um, at our own voltage over that diode. So that will make a real simplification for your analysis. So we will have the midterm examination, and when we meet together in the second next Monday, we will start a new discussion about a new type of device, circuit element, and that element is fundamentally important. Actually, when you say just to say a semiconductor device, PN diode or PN junction up to now is not regarded as the device. But in the second part of our lecture, we will try to deal with how it works and how can we utilize, how can we use it for our circuit purpose. So I think that this first step can be regarded as just a preparation for our second part, and I hope that you have enjoyed these lectures. Okay, time is up, and